Good day, everybody. Welcome to the third webinar of the Fike Explosion Protection webinar series. The topic of today is explosion risk assessment and explosion protection document. And it will give you all the details and examples how an exact assessment of a plant where there is a suspicion of a combustible dust hazard happens. And it will link back to the first presentation that we had on the 27th of April, which laid down the regulations and the steps to compliance. And we will go now in a deeper level, a practical, you have a suspicion of a combustible dust hazard, how to do, what to do, how to go on. And for this, we have our Jeff Davis, Senior Explosion Safety Consultant speaking. Jeff is a licensed professional engineer with a degree in chemical engineering. He has 15 years of experience as a consultant to industry with a focus on combustible dust, flammable gases, liquids, and also process hazard analysis. Jeff is member of several NFPA committees and has previously been a principal member of many of them. I want to ask you to put any question you have in the questions box, and we will reserve time at the end to answer these questions. Also, I can announce that the slides will appear on the website. Also, the recordings of this webinar will be published on the website, as well as any questions unanswered today. You will find an answer on the website within a short period of time. Everyone will be informed with the email address that he has used to log in within a week with all this information. Jeff, I give the word to you. Please go ahead.
All right, thank you, Jim. And thank you everyone for attending. So as Jim said, what I'm here to present on is the explosion risk assessment and the explosion protection document, or the EPD. So kind of a general overview of what we're going to talk about today. We're going to review the ATEX directives kind of briefly. If you tuned into the webinar last week where we went over the regulations, this is somewhat of a review of that. But I wanted to include that. It's important to have that as the background if you were not able to attend that webinar, or if you're new to the explosion protection document. So when I talk about where that comes from, then we'll talk about that explosion protection document, the overview, what's required of it. But then the bulk of the conversation is going to be on conducting the explosion risk assessment. And then finally, we'll finish with complying with the EPD requirements. So where this comes from is you've got two types of regulations for fire and explosion hazards. You've got the safe plant regulations and you've got the safe equipment regulations. So your safe plant regulations, that's directed toward the facility owners. The purpose for this is to ensure workers' exposure to fire and explosion hazards are minimized, generally address operations and facility and building construction. Then you've got the safe equipment regulations that are directed towards the equipment manufacturers to ensure the equipment, machinery, and protective systems are designed to operate reasonably safe in workplaces where explosion hazards can or do exist. So the predominant focus for this presentation is on the safe plant side. Safe equipment kind of comes in a little bit for the risk assessment for ensuring that the equipment's correct, but otherwise we're not really going into a significant amount of detail on that side. So we've got two ATEX directives that we're focusing on. So you've got the workers directive, ATEX 153, so aiming to a safe workplace. So this concentrates the duties on the end users. This includes the requirements for that risk analysis and description, your hazardous zoning locations, your maintenance and operation practices in relation to safety on site. What this is doing is it describes the minimum requirements for improving the health and safety protection of workers potentially at risk. Then you've got the products directives, ATEX 114, aiming to the safe equipment. So as I mentioned before, this concentrates on the duties of the manufacturers and describes the essential health and safety requirements for the products with regard to design and manufacturing. So kind of some examples of standards for explosion hazards. If you tuned into the webinar yesterday that Brian Edwards gave on the dust hazard analysis, that's focused on the US and North America with the National Fire Protection Association. They create the standards there for that. For here, we're looking at European Union standards. We've got the Committee for European Electrical Normalization, and their technical committee, TC 305, develops the EN standards for potentially explosive atmospheres and explosion prevention and protection. So you've also got Germany's got standard, UK has a standard. And now, as we talk about the safe plant regulations, so this is our ATEX 153 that we're focusing on. And the methodological assessment method is the explosion protection document. This is the minimum requirement for all EU member states on explosion safety for plant owners. The UK's got their regulation. The US, like I said, our webinar yesterday on the DHA, where that focuses on the dust hazard analysis for NFPA and OSHA. So to see where these equipment regulations fall in. So again, we're focusing on ATEX 114 for maximum explosion safety requirements for electrical and mechanical equipment brought on market for all member states. US and Canada have National Electric Code, Canadian Electric Code, respectively. And then you've also got code for worldwide territories without their own regulations. So what is the explosion protection document? So ATEX 153 requires the employers who have processes or buildings in which explosive atmospheres can arise to perform a risk analysis to demonstrate compliance by completing a formal documented risk assessment. The explosion protection document, or EPD, is created to show the explosion risks have been assessed once the necessary safety measures have been implemented and documented. The EPD is tested through a checklist followed by further calibration if necessary. One note here that if you're new to this and you're familiar with, say, the DHA that was covered yesterday, the EPD, it doesn't cover just combustible dust. It also is required to cover flammable gases, vapors, and liquids, which can put off flammable vapors. So that's a little bit different, that you're covering a broader range of materials under the EPD. So what must it include? Well, here's the long list of items it must include. And a lot of this pertains to the risk analysis portion that we're going to focus on. So the first part, explosion risks have been determined and assessed. That's going to be the risk analysis. The technical and organization measures put in place to reduce risk of explosions, and measures used to lessen the effects of the explosion. That's what you're doing with the risk analysis at the end. You're coming up with your safeguards and your recommendations and what measures you put into place. Operation of early warning devices. Your classified or your hazardous zone locations, to come up with those, the detailed markings, the maps, identifying these, your signage for these locations, and you're going to do that as one of the steps of the risk analysis. Training and supervision for anyone working in these areas. Operation of permits to work, maintenance, operating procedures, things like that. The properties of the substance that present an explosion hazard. That's the first part of the risk analysis. A means of escape in the event of explosion or fire. Selection and usage of the proper equipment, ensuring that you have the correct CE marked and compliance with the ATEX product regulations. You have the certifications and calibration documents for that. And finally, how often the EPD is reviewed, renewed, and plans to renew in the future. So now what we're going to get into is going to be the explosion risk assessment, and then we'll kind of come at the end, we're going to touch on some of these other items that are outside of that risk assessment, or what you do after that risk assessment. So you got the technical content requirements for an explosion risk assessment, being that description of the process and plant, the characteristics of the materials, that zoning, the identification of your ignition sources, and most importantly, the risk assessment and discussion and justification of measures taken, your protective and preventative measures, and your technical organization measures. So what we're doing here, what my example is going to go through is how we do a risk assessment at Fike. It could be a little different than what you're doing. In my experience with working with European corporations, large, medium-sized corporations with multiple facilities, is they've often got their own internal EPD and risk assessment methodology that they're using, that they apply to all their facilities. So your risk assessment could look a little bit different. One notable thing I've found in a lot of these assessments is they may not necessarily cover severity, whereas ours covers severity, and we'll get into that a little later when I get to that part. But that's it's fine. It doesn't necessarily have to have that. So or be alarmed if you know you have something that doesn't have that. As long as it's meeting these requirements here, you're good with that. But another thing we've seen done is to use process hazard analysis, a PHA, something like a HAZOP, to do your explosion risk assessment. And that's actually, it works really well if you're dealing with a complicated flammable gas or vapor situation. That something like a HAZOP is there. It's a very thorough, very well done PHA. It does take a lot of resources and time to do them, but you do get good results for something like, if you've got complicated, dangerous flammable gas and liquid situations. You can use a PHA for combustible dust aspect. I find it's a little more cumbersome to do that just because the time and constraints on it, that there's going to be an easier option on than a full PHA, but that is acceptable to be used. So our first step on the risk assessment, it's identify all your flammable gas, vapors, liquids, and combustible dust. So predominantly focusing on where they're handled and generated at your facility. However, specifically with the gas and liquids, you do need to focus on storage as well. For your combustible dust, if you've got warehousing of final storage products that just stored in their containers are not being handled, that there's not really a combustible dust explosion risk for like those warehousing areas. I'm sure there can be a fire hazard. If there's a fire in the area, you've got combustible materials, but it's not really at risk of an explosion in storage. Whereas gases and liquids, those absolutely can be an explosion hazard in storage if there were to be a fire. So you do need to consider storage as well. Even if it's bulk storage or you're just warehousing for some flammable liquids for another facility. Now, so you need to get all your characteristics for your materials, and the next two slides are going to go through what those general characteristics that you're looking for the gases and the combustible dust. But your first place to start is going to be the SDS for those materials, and reaching out to the vendors or manufacturers. And I found for the gases and liquids, you can often find what you need on the SDS. It's often going to be on there already, or the vendor or the manufacturer, they'll be willing to give that to you. That's less common with the combustible dust. I do see that becoming more and more common to start including some characteristics of combustible dust on an SDS, but it's not going to include everything. And then contacting the vendor or manufacturer generally doesn't provide much additional information. So that's where you can go to the next step, is look at textbooks and online databases and standards. There's a great German database of test data for many combustible dust. It's a great resource to look for properties. However, you do need to make a consideration when you're looking at other outside resources, and it's not your dust or not yours specifically, that there is the properties for the explosibility properties for dust. It's very dependent upon particle size. So that's why you can look at things like sugar or something like that. And that's a common one. I see that I can see explosion properties that they're all over the place. That it's not the same from one to another, and it's all sugar. And it's a factor of particle size. So usually, like on these databases and textbooks, they're going to have on there what that mean or average particle size diameter was that was tested. You need to know what yours is as well. Is what you're looking at, is it comparable to your product? And if it's not, you be cautious using that. And that's where if you just can't find it, it's not on any databases, or what you found is not truly representative of what you have. That's where you may need the laboratory testing to get your specific data on your powders or your liquids and that. So here's the characteristics we're typically looking at. So this is an example from for flammable gas and liquid from example report we have of, in this case, was toluene. So our kind of main things we're focusing on, we're looking at the flash point, which is that lowest temperature at which the substance emits vapor enough to be able to be ignited. The auto ignition temperature, that's where it can ignite just above that temperature, it's going to self-ignite. Boiling point, vapor pressure. You've got the MEC, minimal explosible concentration, or you might see this reported as LEL, the lower explosion limit or level. But that's the minimum concentration at which ignition is possible. And then you've got the UEL, the upper explosion level, the concentration above which ignition is no longer possible. So in this case here, that's given us the range at what percentage and what volume percent in air that it is explosive. Then finally, we got the temperature class, which is used for determining the gas explosion proof equipment. So verifying that the equipment can never reach a higher temperature than the MIE of the product. And then the gas group as well, which is indication for necessary intrinsic safety of equipment. Then as we get to the dust explosibility properties, as an example for just 3 sample dusts, this is kind of the most common testing we're looking at. There's more that can be done, but this is kind of a good broad range of what's typically looked at. Your first 2 are the Pmax and the KST. So these are used for characterizing the explosion severity properties of the powder. The MEC, minimum explosible concentration, that's defining the minimum concentration of dust suspended in air that can support a deflagration. The minimum ignition energy, or MIE, is the minimum amount of energy required to cause a dust fire or explosion. And so that's good to have when you're evaluating your potential ignition sources, especially like things like static we'll talk about later, that is going to be dependent upon the minimum ignition energy. Then you've got minimum ignition temperature of a cloud, in this case, is what's shown here, and that's the minimum temperature required to ignite a dust cloud. So that's where we want to see if our hot surface is a potential ignition source. But then there also is the layer ignition temperature, the minimum ignition temperature of a dust layer. That's the temperature at which a layer can catch on fire, start a fire. You've got things like conductivity or resistivity that can be done. You've got dust burning rate. There's more that can be done, but this is kind of general starting point for most of these reports. Next, where you got to your next step is to determine your hazardous area or your zone locations, and cover. This defines what requirements of equipment to be installed in those zones. So this is the location in which an explosive atmosphere of combustible dust or vapors or gases occurs during operation. And the zone classification identifies where these exist, and it also determines the likelihood and duration of the explosion atmosphere. So they're classified with zone 0, 1, and 2 for gases, and 20, 21, 22 for dust. And we'll go over those definitions shortly. So as part of your hazardous area classification, you do need to get signage and documentation and your maps, and you're going to indicate your places where an explosive atmosphere may occur. It's indicated with that EX and the yellow triangle, that you're going to need signs that are identifying those locations, where they're at, and potentially the prohibited items from those areas and instructions, things like that. So here's where we get into the definitions for these zones. So you've got gases and vapors, you've got zone 0, 1, and 2, and dust, you've got zone 20, 21, and 22. So a zone 0 or a zone 20, it's a place where the explosive atmosphere, be that gases, vapors, or dust, where it's present continuously or for long periods or frequently. Zones 1 and a zone 21 is the place where that explosive atmosphere, it's likely to occur in normal operation occasionally. And a zone 2 or zone 22, it's a place where the explosive atmosphere, it's not likely to occur in normal operation, but maybe through abnormal conditions, malfunctions, things like that, it could occur. But if it does, it's going to persist for a short period only. So here's kind of some guidance for that grade of release, that continuous, that likely to occur, that not likely to occur. But what I'm going to focus on is that place in that zone. So you're continuous, your zone 0 and your zone 20, where you're inside equipment. I mean, that's where that should be. That should be inside of equipment. You should not have in an occupied working area where you have employees. That should never be a zone 0 or a zone 20, where there are people. That should be limited to inside of equipment. On this likely to occur, this zone 1 and this zone 21, again, that's generally going to be inside of equipment. However, if there are problems with your operations, it could be in those areas. And it's also likely to be in areas at kind of small radiuses where you're have open powder handling in that. And I've got that in an example coming up. Or you might have a very small zone 21 location, for example, within while the rest of the room is zone 22. And then that zone 2 or that zone 22, that's most often going to be your occupied areas outside of the equipment where the processes are. It could be in equipment if it's not generally going to have actual combustible dust present or flammable gases present, but it could be there minimally. Now, if you're more familiar with the NFPA class division system, that where you have class 1 and class 2 for vapors and class 2 for dust, and division 1 and 2. A difference with the ATEX is the ATEX thing, as I've kind of gone through, we talk about it's a zone 0 or 1 or 2 or inside of equipment. The NFPA's class division system is not made to be applied inside of equipment. That applies to the locations only. So that's kind of one key difference between these, that when you're doing your risk ranking here and your risk things that you are going to identify, you're going to assign a zone to everything inside equipment and outside equipment. Now what I've got here is a zoning example here, and that this is a powder handling operation. So you've got manual powder dumping from a small container to a small feed hopper at the top. That in that little small space, it's a zone 21, right? Where that right around the top of that filler and in that container, because you're generating, so a little bit of dust is going to be generated in that area, but it's going to be very localized to that area. And then you've got the outer radius here of a zone, the zone 22, because you said you shouldn't really be getting a dust cloud there, but if there's a malfunction or if this material isn't handled properly, that you could have a further dust cloud out here. And it should not occur it should be for a short time only. That material is going to go through a rotary valve and into a feed hopper, and this feed hopper is going to be a zone 20 because it's continuously, you've got a dust cloud being generated as that material drops in there and fills. It's going to create a dust cloud in there. Now that powder, as it settles, it's going to go through another rotary valve and into a product container where, again, you've got a very small zone 20, kind of as it falls right into that localized point, but the rest of it's a zone 22. Then also here, this feed hopper's got a filter for that displaced air when it's dropping down, which does help minimize that dust cloud. That it's going to go through the filter, and that air is going to be pulled off. But that on that clean air side of that filter, that's going to be a zone 22 as well, because if there was a malfunction in the filter or the bag broke, something like that, that you could then have a dust stream going through that ducting. So there's an abnormal condition or a malfunction could introduce dust into that line, whereas normally you wouldn't expect to see that. The next example here is kind of your overall zoning layout maps. And in this case here, what we've got is a rail unloading example. Rail cars are unloaded. So you've got a pit that's a zone 21, and then you've got the rest of the area that's a zone 22. So you should create these kind of maps for all of your areas. If you have like process flow diagrams and P&IDs that show equipment and you've got good drawings of that, you can create something like this for all your processes where you're going to hatch all those zones on all the equipment lines. If you don't have that for some of your equipment, at the very least, if these tanks here and these bins, if they're holding flammable or combustible materials, and if they have a rating, apply that rating here on the map. And that way you're identifying where everything is, where all your zone locations are. And this should be posted, should be part of your EPD and should be posted at at those areas as well, so everyone is aware of the zone ratings. Now we're going to transition to the ignition risk assessment portion of this. And what we're looking at, there's 13 recognized ignition sources from EN 1127-1. Things like hot surfaces and electrical equipment and static and chemical reactions, things like that. So we're not going to go through every single one of those. I'm going to focus in more detail on what's the most common ignition sources that we find. Things like ionizing radiation, ultrasound, and electromagnetic waves are not commonly found, and especially when we're looking at the dust side of things, they're not common ignition sources. So I just really want to focus our time on what we see as most common. So we got mechanical sparks as an example. So this is that impact or friction with metal that generates sparks. So common sources, that hammer mills, pulverizers, grinding equipment that can create mechanical sparks, either just if it's operated incorrectly, if it's not in alignment right, or parts can break off and create sparks, or you can have those foreign objects that are down here that could come in and that creates sparks. You can have rotating pieces of equipment like the fans and conveyors, blower packages, anything that those air moving devices, if those rotating equipment gets out of alignment and is damaged or hitting the housing, that it can create sparks. Then you've got the foreign objects, which could be like foreign debris, metal or rocks that come into your material stream. But it could also be those things like the example here of a broken impeller blade, that when that breaks off, that you're sending that tramp metal gets sent down into the system, and that can create sparks on the conveying lines. It could create a hazardous spark if it hits a mill down the line, or if it hits the receiver or bin that it goes into. Then finally, you've got cutting, metal grinding, and drilling. Now, frictional heat and hot work. So frictional heat can be generated when you're on your process itself. If you're sanding, routing, cutting your material, that can create frictional heat. But you can also get it within equipment. Bearings are a big one that historically have been a huge source of fires, and in some cases explosions, from overheating of bearings. And a lot of times, especially newer equipment, the bearings are separate from the product stream. The bearings generally aren't going to be in your material stream. They're going to be outside of that. However, they can still, if they overheat and catch fire, that it can still then create a hot surface inside the equipment if it's not caught and put out. But then you've got things like conveyor belts and bucket elevators and screw conveyors, where if they're operated outside of their alignment, if the belt gets off or the screw conveyor's damaged, that it's rubbing the housing, that just in its process, even things like a screw conveyor that's not moving that fast, that maybe it's not moving fast enough to create a mechanical spark, but it can keep rubbing against that housing. It's going to generate frictional heat and create a hot surface. Then we've also got hot work, like welding activities. So it's maintenance activities that generate heat, and you have to have hot work permits for those in hazardous locations. And we'll actually talk about towards the very end, we're going to go into a couple of the permit requirements. Electrical equipment. So there's multiple reasons why electrical equipment can be an ignition source, being the direct electrical current, arcs, or even overheating of equipment. So improper mounting and maintenance can cause electrical shorts, sparks, and overheating. Electrical equipment used in hazardous locations must be rated for the location, and we'll talk later about that ATEX 114, where you have to have the correct equipment. And as you can see from the example here, everything here is wrong. Based on the dust that's present, that's at least a zone 22, and none of that equipment is going to be zone 22 rated. It's not stamped, it's not certified, so it's the incorrect equipment. Another example, and it's a pretty bad example, though. Okay, this is a really bad scenario of we've got a lot of dust, so this is zone 21, 22 location, obviously not rated equipment. But I use this example to talk about that if your area is zone 20, is zone 21, zone 22 is rated, and you have the correct equipment, and you've got the correct electrical disconnects and receptacles and things, that they're certified if they're operated correctly. If they're open, they're not operated. And I see that a lot with explosion-proof equipment, zone 0 and zone 20 equipment that's going to have those massive bolt patterns that hold the enclosure together. That a lot of times you'll see that if things have been if maintenance has gone on, that sometimes all those bolts aren't put back. At which point that's no longer rated for that location. This one's pretty self-explanatory, but open flames and hot surfaces, so pilot lights, boilers, dryers, anything that's heated, but also consider light fixtures, even motors that can overheat. Static electricity. So the three main types that can ignite dust clouds. So you've got spark discharges, the bulking brush or cone discharges, and propagating brush discharges. Really what this occurs is when two electrically conductive objects on a different electrical potential. So you have a charge built on one object, and then the charged object touches another object, and then the electric charge bridges that gap. So you think of if you're just rubbing your feet on a carpet and you touch a doorknob and you get shocked, that's a spark discharge. But kind of for these bulking brush and propagating brush discharges, that's like a bulking brush is where the charge builds on the powder itself, just as a method of when conveying into bins and receivers, things like that. And then a propagating brush discharge is kind of where your charge builds up against the non-conductive, say, flexible hosing and conveyance lines. So the amount of charge that can build up on an object is going to be dependent on the size and capacitance. So we've got a table here that kind of just to put things in perspective. So a flange, something very small, it's got a very low capacitance. So the maximum MIE of a concern from a spark discharge of a flange is going to be 4 millijoules. So for most combustible dust, your MIE is well above that. There are some that will be below that, but by and large, combustible dusts are going to be higher than 4 millijoules. However, your flammable gases and vapors are going to be much lower than that generally. So at that point, so for flammable gases and vapors, any of these could be a concern. But for your combustible dust, maybe not as much of a concern with flange. But if we go to the operator, that means the person that's maybe handling those powders, maybe the person that was in our earlier example that's dumping those powders into the hopper, maybe he's using a scoop or just dumping bags. The capacitance on a person is going to be 150, which puts a max MIE of concern of 30 millijoules. So if you know you're handling combustible dusts that are less than 30 millijoules, then you need to consider grounding on that operator, be it grounding straps on the person or conductive footwear, anti-static flooring, something like that to control those static risks. Then you go all the way down to like tanker trucks and think of something much bigger that at that point is going to be able to ignite just about any combustible dust. So size matters on where it will ignite the combustible dust. Again, the flammable gases and vapors are much more easily ignited to where any of these can be a concern. Now we're going to kind of the consequences of events, and this is where we get into the severity and kind of what I talked about earlier, that I've seen some companies don't include severity in their risk assessments, and that's fine. We like to include it because it helps with our risk ranking. If you don't have the severity, it gets a little bit more difficult to prioritize. So in our scenario here, we've gone through, we've done the zoning locations. We found where all of our locations are. We've assigned them a zone. We've then gone through, found what all of our ignition sources are and assigned likelihoods to those. Now we got to look at these scenarios here. Like, what are the safe operating parameters for the equipment? Are there engineering controls or safeguards that are in place? Do we need additional controls? What types of equipment and occupancies are near the location of the hazard? That's going to affect your severity. What pieces of equipment are connected via ducts or conveyors? That gets into the next point of the potential chain of events. If you've got if you have an explosion in a dust collector or a vessel, a bin, what's connected to it? Is it set up in such a way that you can have explosion propagate upstream to that, downstream to that? Where's that Where's that chain of events occur? Does it rupture into the area where there could be people? Where does that end? So that plays a role as well. So that gets us to the risk. And again, so we're using we've got kind of a three-dimensional model where we're looking at the ignition, the atmosphere, and severity. So if you're not focused on severity, you've got a two-dimensional model, and that you can still determine your unacceptable risks in those locations. So in our case, our risk is determined by the specific fire explosion hazard based on likelihood and severity. So we want to look at the potential for that ignitable atmosphere. In your locations, the big thing is going to be electrical equipment. Is that electrical equipment appropriate for that location? Do you have screw conveyors, bucket elevators? Do you have things with bearings? Do you have bearing monitors? Is that a potential? Static, certainly a big one, as we just showed. Then those being those ignition sources there. You got to consider all operating modes, the normal mode, abnormal, startup, and shutdown, because there can be variations there. That in normal operation, you've got it all clear, but what scenarios, if something malfunctions, what's going to happen? Are you covered for that? So if you're looking at severity, what it needs to consider first and foremost is the potential harm to employees. That's obvious on that. But second, you also got to look at the impact to the business for downtime, because that can be increased severity as well. We can use an example of if you have a remote operation where there's no employees there, it's all run remotely, no one's there. If you have a fire or explosion, there's no harm to employees because there's no one there, but does that shut you down for weeks, months, years? I mean, that's an impact to business if you can't operate. So if you're going to be shut down for an extended period of time, but no one was hurt, that's still a high severity. Then also going to look at those existing safeguards you have in place. So from our risk ranking perspective, we're using risk groups and a risk ranking where we go from 1 to 125, and that's by looking at that atmosphere, that ignition source, and that severity. And so we do this so that we can provide a ranking for recommendations. So you can prioritize what your actions are going to be. If you're not looking at severity, again, it can be a little more difficult just to figure out your priority, but you can still you can still assign a priority, but it can be a little more subjective. So once we have this explosion risk assessment completed, you've got a risk matrix that should be identifying areas and equipment that are at unacceptable levels of risk. Now you need to come up with the recommendations to reduce that likelihood or that severity for everything that's unacceptable. So we can have, in some cases, there may be multiple options. I can use the example of looking at some of those pictures before with the dust with the electrical equipment. Let's say you have a location that's a zone, it was designed as a zone 22. All of your electrical equipment is a zone 22. You've got the certifications, you've got everything for that. But now through a process change or just problems with the operation of the product, that it's now you've got dust accumulations, you've got leaks, you've got dust clouds, that now it's a zone 21. So you've got two choices there. You can either fix the equipment, fix the problems what's going on. That might be increased maintenance and housekeeping and change of operational procedures to get it back down to a zone 22, or you can upgrade your electrical to upgrade all your electrical so it's zone 21. But then also in some cases it's if you're looking at severity, what can you do to reduce the severity if there were to be a fire or an explosion? Then coming up with your priority of recommendations, it should be based on a balance of which items present the greatest risk and which recommendations are most feasible. No company's got unlimited money and resources, so you can't do everything immediately at once. So you do need to come up with an action plan that's going to tell you where you're going to implement these things, when you're going to do it, who's responsible for it, things like that. Then we get into the risk assessment's going to have recommendations for additional safeguards potentially, and I'll point out that so we've got a webinar next week that's going to cover these risk reduction methods. But I'll kind of just brief overview of what those are, what they can be. Like engineering controls, you've got active ventilation, and that's going to be things like dust collection for powder handling operations, but it also includes ventilation for room ventilation or process ventilation for if you're transferring flammable liquids, or you've got battery charging stations where you could have the potential for hydrogen gas generation. That active ventilation is controlling the concentration in the room. It's creating the appropriate air changes that you're not reaching a hazardous atmosphere. Ignition source reduction, so that could be things like your grounding and bonding programs. It could be bearing monitors, vibration temperature monitors, belt alignment, things to control some of those frictional or mechanical sparks. Finally, there's explosion protection and isolation, which is you're going to run into situations, and a good example of this is a dust collector, that you're going to run into situations where you cannot eliminate all the potential ignition sources. So to use the dust collector as an example, that's going to be a zone 20. You've always got that. By the nature of its operation, you have a combustible dust cloud present. So if it's a zone 20, you have to control every ignition source so it never occurs. And that's not going to be feasible in all cases. That there's always going to be something that could occur. It's not likely, even if it's not likely to occur, but it could occur during the life of the process. And that's where, okay, well, the only scenario you have is to install explosion protection and isolation on that equipment. Then we've got administrative controls, so that's housekeeping plans, maintenance programs, inspections, safe work practices, your operating procedures. Then also it might recommend hazard communication and training if there's deficiencies or updates are needed to that. All right, so now you've got the assessment done. Real quick on the ATEX equipment, so ATEX 114, this is where the equipment manufacturers determine the category of equipment. They do a hazard analysis and risk assessment. If it's category 1, some category 2, they have to submit for testing and certification by a third party, and then they mark the equipment with the appropriate CE and EX symbols. So we talk about the ATEX markings, and I borrowed this slide from the presentation last week as it was better than the one I had, but it's going to go over this. This is your ATEX marking. So if you've got a hazardous location, all of your equipment, all your electrical equipment, it has to have these stamps on it. That's going to identify the explosion protection, equipment group and category, the environment for it, is it gas or dust, protection type, temperature class, things like that. Everything has to have that in a rated location, and there should be documentation that goes along with it. That could be certifications, there could be calibration documents. You need to maintain all of that in your EPD, and it's on file for these here, for anything in those hazardous locations. Then we'll talk about training. So this first part, this is directly from the ATEX directive. So the employer must provide those working in places where explosive atmospheres may occur with sufficient and appropriate training with regard to explosion protection. So what I say here is that general safety training and hazard awareness training for flammable gases, vapors, liquids, and combustible dust should be provided to all infected employees. It's a general awareness training. It should cover every employee in a location that has a hazardous atmosphere. Then you'll get to job-specific training, so ensure that the employees are knowledgeable about fire and explosion hazards in their work environment. So that's going to get into what they need to know specifically to do their specific job safely. So here's some items that it should include. You should include the hazards of that environment and procedures in case of emergencies. So obviously including fires and explosions, but also what about hazardous material releases? Include that as well if that's applicable to where you are. The operation, inspection, testing, and maintenance procedures that are applicable to their assigned work. Maintenance especially, as they might be opening equipment. That is there protection equipment on here that needs to be locked out first? Are there things that can it be safely opened this way? Those procedures that they need to have. Also, if you have personal grounding and bonding stuff for personnel, that may be different for the maintenance, for them working on it, that ensure that you have those right procedures there. You need your normal process procedures, but also emergency procedures and changes to procedures that those operators are trained on. You have emergency response plan. So that's safe and proper evacuation. You should have your evacuation maps and training on that, as well as permissible methods for fighting incipient fires in work areas, if that's allowed by your company. The necessity for proper function of related fire and explosion systems, the safe handling, use, and storage of materials that they generate, locations, operations of your protection equipment, your fire alarms, your emergency phones, safety equipment, first aid, things like that. And then finally, just overall operations, safe startup and shutdown in response to upset conditions. What do you do? What are your emergency stop procedures? Things like that. Then we get to those written instructions and permits to work. So again, this first part is directly from the standard where work in hazardous places must be carried out in accordance with written instructions issued by the employer. System of permits to work must be applied for carrying out both hazardous activities and activities which may interact with other work to cause hazards. They have to be issued by a person with responsibility prior to commencement of the work. So some examples is the work in areas where a flame or spark is prohibited. So that's those hazardous locations that you can't bring in something that's going to generate a spark, including electrical equipment. Anything that goes in there has to be rated for that location. The hot work we talked about earlier, that welding, things like that. You need hot work program to do any of that in those rated locations. You may have confined spaces, so you need permits for confined spaces. Working on electrical installations, whether they're live or dead, that should be permits related to that. But this also talks about written instructions. It goes back to that talk about operating procedures, that you should have written operating procedures for your operation that covers that startup, that shutdown, normal operation, but also abnormal conditions and emergency shutdown. So you need to have those procedures in place and then review them with the operators. That's part of their job, is that they have these procedures and they're trained on them and they know how to operate safely. And finally, we've got the EPD review and renewal or revalidation. So EPD must be kept up to date. This should be considered like a living document. It needs to be drawn up prior to the commencement of work, and then you revise it as anything changes that impacts it. So if you're changing the workplace or the equipment, process changes, material changes, things like that, this needs to be updated as part of that. So you're starting up a new facility, you're generating this document as construction's going on, that it's in place prior to starting operations. If you're going to add new equipment, you're updating this as you're adding that equipment. It is in place. Everyone's trained on the procedures and the hazards and prior to starting up on it. And then you should do a periodic renewal revalidation. I think most companies tend to do them on a 5-year basis. If you do everything and keep this completely up to date and it's a living document you're updating all the time, when you come to that renewal or revalidation time frame, you probably shouldn't have a whole lot to do because it should already be up to date. But it's very important to do that. So don't think, oh, we do it all the time, so we don't need to do a full revalidation. You should, because sometimes there's little small changes that come through, maybe a change in the regulations or just a common work practice change that didn't think it would impact things. But you go through that whole revalidation renewal, that will, you might find things you missed, things that weren't kept up to date. And that's important to include that. So that's kind of the end of my webinar, but just I want to point out that we've got in the next 3 weeks, we've got, especially talked about the one next week on risk reduction methods. And then after that, we've got explosion protection for dust collectors, and then following protection on bucket elevators. I want to thank you all for attending and for your time, and I'm happy to take any questions. And for more information, you can go to our website, you can send me an email. We're happy to answer any questions you may have. And I'll turn back to Jim if there's questions.
Thank you very much, Jeff. This was a very interesting presentation. I found it clear, a good overview of all aspects with examples to illustrate the more abstract concepts. So thank you very much. There are a couple of questions. We have time. We have still 10 minutes. We will pick these questions. Everything that stays unanswered today will be answered and will be published on the website, for which you will receive an email with a link. People that had followed the previous webinars will receive today a link with questions and PowerPoint links to the previous webinar. So that will come today. For this webinar, it will follow within the next week. All right, let us see what we have. Question number 1. Are there template assessment tools, for instance, data collection tables, etc., that provide an organized means to gather and then analyze the data?
That's a good question. I know there are some. Let me check and look into, make sure we find those. If there's ones, make sure they're good ones. So that might be a better one we can follow up later. I'm gonna check with a couple people and what's a good template to use, because I know I've seen lots of templates and they're not always that useful. That they sometimes make it something easy to look. It makes it easy to see what that you're going through the steps, but they make it easy to miss things or mischaracterize things. So let me do actually a little research on that if there's some good examples worth sharing.
Great. We will then publish these on the answers sheet. The second question, are you seeing an increase in US companies adopting these ATEX requirements and requiring their own zoning maps?
Okay, yes and no. So we see a lot of this, especially for European companies that operate in the US or North America, so in Canada as well, that they implement these requirements here, to implement them for the US, where you're assigning these zones. And you can do that. NFPA allows for equivalency, so you could use those zones. NFPA already has their own standards for doing maps and for posting placards. The ATEX is much more thorough in what it requires, so it's a very good idea that for US companies to adopt that approach of identifying your zone locations, which again, and if you're not a European company, you're probably going to be using the class division system. So it's at least documenting, identifying these maps for where you have a class 2, a class 1, division 1, division 2 location, where at the very least you're doing that. And we see more of that, and it's a very good practice, and we'd recommend that.
Thank you, Jeff. The next question is the following. Could you define levels of likelihood of ignition and likelihood of atmospheres? So I guess not maybe numbers, but levels like level 1, 2, 3 or whatever.
Yes, and I've seen that a lot. So that's where you can, it works well on use a 3x3 of 1 through 3, or a 4x4. I guess you could use that, where you have a occurrence of, for your atmosphere, you've got let's use dust as an example. So 20, 21, 22, or not rated. So that's your likelihood on one side you can assign that a scale of 1 to 4. And then you go to your ignition sources, where you can use a scale of 1 to 4 or 1 to 3 here, where it's that it doesn't occur, or it does have that it's likely to occur. Like we see a lot where it's a very rare occurrence, where it's okay, this may happen once, twice in the life of the process, not expected to happen more than once in 20 years. Then you can go to, okay, then it's a rare occurrence. Maybe it happens once every 10 years, once every 5 years. And then you go over to that common occurrence, where, okay, this happens all the time. It's the nature of its operation. So when you do things like that, you can create your scale to plot your risk, and that's a common methodology, and that's similar to the scale we're using at Fike.
Yes, that is clear. Thank you. The next question, does Fike offer any independent reviews of systems regarding zoning?
Yes, we can. I think I understand what they're asking too. That if you have established that your location's a zone 22, that you want to have an independent review to review your process to make sure that that is correct. I assume that's what it's asking. And yes, yeah, we can certainly do that. That's I said we're doing an assessment of, and what that includes, what that is it's look at that process. Is it fully contained? Are there open materials? Are also, but even in the equipment itself, is that rated appropriately? That is certainly something we can accomplish.
All right. Someone else asks the following: does the hazardous area classification varies with the distance at which a device is located to the hazardous zone?
You say it again?
Does the hazardous area classification varies with the distance at which a device is located to the hazardous zone? I think meant
Yes.
the origin of the flammable substance. No.
Yes. Yeah. So that, yeah, that would be done. That, so like in that earlier example of that small powder handling operation where um, you have open powder handling, that in that immediate vicinity around where you're handling that's a let's say a zone 21, and then you extend that, everything around that then is a zone 22. In some cases, depends how your operation is, that you may want to, if you've got multiple pieces of equipment, it's preferred that are in one room. It's preferred you just rake the whole room, so you're not having to identify these radiuses on the floor. But if it's a big area and this is the one thing, then yeah, you would look at what those radiuses can be. It can depend on the materials that you're looking at. A default on a zone 22 is generally, I think, 10 feet. So we're like 2 to 3 meters, I believe, is the default for those classifications. But you have to be careful of that as well, that where that typically applies is the extent of where dusting stops. So it's not always where that equipment ends, from where that source is. You would go out 3 meters, say. If the process does generate some dust and that you do see light dusting on the floor normally, then you want to actually start your radius at where that dusting normally stops. So it could be, it will vary. It could vary on that, where those ranges go.
Mm-hmm. We have time for a last question. All the other questions will be answered offline. But what is the recommended mandated period for an EPD to be reviewed, revised? I thought you said 5 years. I'm not. Is that a regulated number, or that's my personal thought with that question? But question is, what is the recommended mandated period for an EPD to be reviewed, revised?
Yeah, it was. So the directive itself does not specify a time frame. What I've seen, what most industry does, is a 5-year full reevaluation. That's similar to the U.S. standards for the DHA, where that has to be done every 5 years. So a full review or reevaluation should be done at least every 5 years, but you also should check with your corporate requirements that if you requiring it more frequently, then you need to meet that. But it's not a bad idea to even annually do some level of review. Pick a process, especially if you've got a really big process. It can be very daunting for that whole revalidation, that maybe you do want to break it up into sections that you're going to look at. We're going to focus on process A for this year. We want to look at this in more detail. And that's a good opportunity to review those standard operating procedures too. You should be reviewing those at some frequency. Again, like we tell most people, it's like maybe you want to review those at least annually, that you're going to look through those processes, that it helps check if are people doing the job the correct way that it says they're supposed to do it. Is something changed, something missed? Have they found a safer way to do it and it's not documented yet? That's where all those things are important, and that's why that renewal is important.
Understood. So we come to the end of this webinar. I would like to thank everyone for your attendance, and we welcome you to the next week's webinar on the explosion mitigation and prevention methods, and wish you a further good day. Bye-bye.
Bye, thanks.